I'm going to be solving for the last step of the linear wave equation using these bounds and solving for a sub n within this general solution. Now this general solution is the solution you arrive at by using the three different cases in the wave equation from your boundary conditions given up here in the top. I'm going to be using this fourth equation, this nonlinear equation, to be solving for a sub n in the summation.
Quick note from future me, this should actually be n equals 1, 3, 5 here, and this should be infinity on the top, instead of n and k equals 0.
So before I get started, it's important to know what the boundary condition is actually telling us. This is telling us that for u, where x is equal to x, and t is equal to 0, the equation is going to come out to the solution x for x is larger than 0 and less than pi. So down here in the summation, we can actually plug in 0 for t. And as we know, cosine of n times 0 over 2 equals cosine of 0, and this equals 1. So we can actually cancel out this entire last term because this equals 1. And this is the solution that we're working with when we take the integral using the Fourier series definition. So to solve for a sub n, I'm going to write an integral down below. A sub n equals 2 over pi, and this is because our boundary condition is from 0 to pi. And this is multiplied by the integral of our initial boundary condition, 0, to the upper boundary condition, pi, as shown up here, 0 to pi. And we're going to substitute x in for a sub n in this case, because this is where the solution is equal to x. Say over here, this was u of x of 0 equals 1, we would substitute 1 into a sub n for this case. But for this boundary condition, we have x. So let's put an x down here, and our next term is sine of n x over 2, and this is integrated with respect to dx. So now all we have to do is solve this integral. And this is integration by parts. We can put a line down here. This is our f term, this is our g term. And as we know by integration by parts, the integral of f g prime equals f g minus the integral of f prime g. So that actually makes this g prime in this case. So over on the right, I'm going to write our f term is equal to x, f prime equals 1, g prime equals sine of nx over 2, and our g term is going to be negative cosine of nx over 2 divided by n over 2, and this is really equal to negative 2 cosine of nx over 2 over n. So this is g. So all I did here was bring the 2 up into the numerator. Okay, let's go ahead and plug this back into our integral. So we get a sub n equals 2 over pi times f, which is our x, times g, which is negative 2 cosine nx over 2 over n, minus our integral from 0 to pi of f prime, which is 1, times our g term, which is once again negative 2 cosine nx over 2 divided by n dx. And this is all integrated from 0 to pi. Okay, let's go ahead and clean this up a little bit. A sub n equals 2 over pi times negative 2x cosine of nx over 2 over n minus negative 2, and the integral of cosine is sine of nx over 2 divided by n times n over 2 because we send this back down to the denominator, and this is all evaluated from 0 to pi once again. So a sub n equals 2 over pi times negative 2x cosine nx over 2 over n minus 4 sine of nx over 2 over n squared. Once again, evaluated from 0 to pi. And once we go ahead and plug in our pi and our 0, we get a sub n equals 2 over pi times negative 2 pi cosine of n pi over 2 over n minus 4 sine of n pi over 2 over n squared. So keep in mind that cosine of pi over 2 is always going to be equal to 0. And because of the properties of cosine, no matter what we multiply this beginning number here by, whether it be 1, 2, or 3, this is always going to be equal to 0. So what this actually allows us to do is cross out this entire first term here, because cosine of pi over 2 is always going to be 0, and multiplying any of these by 0 is going to zero that out. We can't do the same with the sine term, unfortunately, because this will never equal 0 for us. Also, just a quick note, these should actually be positives. After looking back at my work, I had a double negative that I missed the plus sign on, so this should be a positive. Alright, so now we're good to go. Now we can solve for a sub n and simplify this a little bit more. So this is equal to 2 over pi times 4 sine of n pi over 2, and this is over n squared. And now we can put in that 2 over pi, which gives us a sub n equals 8 sine of n pi over 2 over pi n squared. And this is our solution for that coefficient up in our problem earlier, up here. And now we can actually go straight ahead and plug that in for u of x of t. So after plugging back in, we get u of x of t equals the summation from n equals 1, 3, 5 to infinity times 8 sine of n pi over 2 over pi n squared. And this is our a sub n term, and this is multiplied by sine of n x over 2 times cosine of n t over 2. And this is our solution for u of x of t. And the cool thing about solving a sub n like this is you can find any nth term of a sub n. So say you want a sub 3, and this is going to equal 8 sine of 3 pi over 2 over pi times 3 squared. And this is going to give us negative 8 over 9 pi for the third term of a.